and welcome, strange people of the internet. I am Kiara Blows. I am a biomedical sciences student at Newcastle University, and I'm going to be your physical sciences tutor with Tutorbox Live in conjunction with COVID-19 catch-up courses. So I hope you are as excited as I am to get our think on. You know, this lockdown is just, you need to engage your mind. Right, we know that. So I know a lot of people are very intimidated by physical sciences, and it is said to be the most difficult subject, maybe. And it definitely does have its difficulties, but I think you just have to know what to look out for, tips and tricks, which I will definitely share with you. And who knows, maybe you'll get the marks you've always wanted, which I believe in you, 100%. And so I just wanted to I'm so proud of you for taking the time out of your day to sit here and listen to what I have to say, because I'm not a very interesting person, but I can help you with science, so we'll go with that. And yeah, so grab your notebook, probably your worksheet that you were sent with us, some writing materials, your willpower and your brain, and perhaps a very caffeinated beverage, and let's get started. Welcome to your second lesson in physical sciences, and today we are going to be covering chemistry and specifically chemical bonding. So firstly, we are going to discuss bonding and valence electrons. A thing to remember is whenever you do any chemistry is to have a periodic table of elements. There is a reason this is a tool for all your chemistry and why you should have it before you sit down to any chemistry lesson or exercise or even your exams, because it provides valuable insight to almost all of the sections. So firstly, when atoms combine, the electrons involved are called your valence electrons. These are on the highest energy level or in the outer shell of an element, and the number of electrons in the atom of an element is equal to the group number. Okay, so hydrogen has 1, lithium has 1, carbon has 4, etc. The number of bonds an atom can form is referred to as the valency of that atom. For groups 1 to 4, the valency is the same as the group number, so 1, 2, 3, and 4. But for groups 5 to 8, the group number is equal to 8 minus. So if you think about it, we've got 5 electrons here, so therefore we only have 3 spaces left. Okay, so there are 3 main types of chemical bonding. So we have metallic, and this is when the particles in a metal are held together by your metallic bonds. It's a strong attraction between closely packed positive metal ions and a sea of delocalized electrons. This is what allows the properties of the metal to have a high melting point and boiling point, as well as be allowed to have the property of conductivity. Ionic is the bonding between positive and negative ions, and these are held in place by the electrostatic attraction, and they form an ionic crystal lattice. Your valence electrons are transferred in ionic bonding, so one ion that's positive will generally gain, and the one that's negative will generally lose. Okay, so the result of the ions having charges, so they're positive or negative, and your non-metal is normally negative and your metal is normally positive. Lastly, we have covalent bonding, which is formed between non-metal ions. Your valence electrons here are shared, not transferred as in ionic. So this sharing holds in place and is called a molecule. So the half-filled orbitals have to overlap, and your electrons have to have the right spin to result in the bonding pair of electrons. You don't have to really know that as of right now. Just be aware of that concept. Your covalent bonds can be single, double, or triple. And if there are other pairs in the atom that are not shared, these are called your lone pair of electrons. And the types and number of atoms in a molecule are shown in its formula. Okay, so we're going to focus on covalent bonding now, and specifically how to notorize it. So the Lewis notation is most commonly used, and I'm sure you remember being taught this in the start of the year, or even last year. So your electron pairs, which are being shared, are drawn as dots and crosses between the two atoms sharing them. You always fill the octet, so remember you've got your element, and you've got 1, 2, 3, 4, 5, 6, 7, 8 around it. And you use the valency or group number. Cooper notation is another method used, which is basically just an elaboration on Lewis notation, where the shared electron pairs are represented by the line, and you don't draw all the other electrons. So I'm going to ask you to attempt the following examples in both notations. The worksheet should have spaces for you to fill in both. So we're going to do H2 or hydrogen gas, HCl or hydrochloric acid, NH3, CO2, and nitrogen gas. Before you do that though, I'm just going to mention dative or coordinate bonds. So this is when the atom has an incomplete complement electron in its valence shell. And having this property means it can share a lone pair of electrons from another atom to form a dative or coordinate covalent bond. So the examples are going to be ammonium and hydronium. Attempt these two just as a bit of active recall, and then I shall go through the answers in detail with you. H2, sorry. So used to just saying H2O just rolls off the tongue. Okay, so as you can see by the red arrow, that is your electron from that hydrogen atom. And then this electron is from this hydrogen. So we use dots and crosses, remember, just to differentiate which ones come from which. And they would be joined together for your Lewis diagram. However, for your Cooper, remember, it is drawn as a straight line. Alright guys, so welcome back, and I hope you had a good attempt at these. We're just going to go through the answers in detail, and if there are any queries, please flag them up and we can go through them in the Q&A, which will be live after this. Okay, so first we've got H2O. No, we don't. HCl. So remember, we've got 1 electron in your hydrogen, and we've got 2, 4, 6, 7 in your chlorine. Okay, we got that from our periodic table. So we draw, this is just how you would draw it before, like a step before. Your final version will be that circle there and your H next to it. And then your Cooper notation is with a straight line. Okay, next one. So this was in H3. Also, just to note with the Cooper notation that there's no lone electron pairs. So in the other one, there's only one line. There's not showing all the others from the chlorine. Okay. And next we've got nitrogen. So remember that's group 5, which is why we've got 5 electrons for nitrogen. All of the hydrogens contribute 1. So this will be your step before, and your final step will have your electron there in your H, electron there in your H, and your electron there in your H. And then Cooper is all just the lines where the shared bonds are. Okay. Next we have CO2. So carbon has a valency of 4. And remember how you write this is you have 1 on top, 1 on side, 1 on the bottom, and 1 on the left. So you always think of it as we've got 4 spaces, I suppose, and 2 electrons can fit into each. So we always start clockwise. Is that clockwise? Yes, that is clockwise. Don't know if it should have clockwise for you, but you always go clockwise, and you just fill in 1 each. So you don't go 1, 2, 1, 2. You always go 1, 2, 3, 4, and then if there's extra, you put on top. Okay, and then we've got oxygen, which has 6. Okay. However, in this case, what's going to happen is your carbon is going to contribute 2 to each oxygen atom. Okay. And then we write it out as this is our final. So we've got the shared double bond. Okay. Or shared double electrons, which make your double bond. And then your Cooper notation has them just as lines with no lone pair electrons. Okay, then the next one was N2. Okay, so each nitrogen, remember, has 5 valence electrons. Okay, and then what's going to happen in this one is you're going to share 3 because it can. And then you're going to have a 2 on the outside. And then your Cooper will just be 3 straight lines. Okay, and then we've got ammonium. So these X electrons come from your hydrogen, so that's why there are 3. And your nitrogen, remember, has 5. So we've got a full octet. However, it's NH4, so we have an extra H. All that means is the H attaches to these 2 lone electron pairs, and it doesn't contribute any electrons itself, but it does contribute a charge. Okay, and that's why you see that over there. Next one, H3O+, or hydronium. So we've got these 6 from the oxygen, and these X's are contributed from your hydrogen. This hydrogen does not contribute any electrons, and that's why it has a positive charge. Okay, and now we're going to move on to the next section. Okay, so our next little section is going to focus on electronegativity in your covalent bonding. Okay, so what electronegativity is, this is a definition, and like I've said before, and I will continue saying, make notes of your definitions, keep them in one place, and make sure you revise them before your exam. It is the measure of the tendency of an atom to attract the shared electron pair towards itself. On the periodic table of elements, the electronegativity increases from left to right in a period and decreases from top to bottom in a group. If you have your periodic table in front of you, make a note of that. In a polar covalent bond, there is a difference in electronegativity between the bonded atoms. For example, in HCl, the bonded pair is attracted closer to the chlorine than to the hydrogen because chlorine is more electronegative. The molecule is a polar molecule. So all that means is polar means it has poles. So because the chlorine attracts more strongly, it'll be slightly negative, as it says, chlorine slightly negative, and the hydrogen will be a slightly positive. Okay. You will see your electronegativities on your periodic table, which is why it's so important. If the electron pair is shared equally, however, they have the same electronegativity, then this is called a pure covalent. So there won't be any slight positive or slight negative, and so there are no poles, and the bond is called non-polar, and it can form a non-polar molecule. Okay, a little more on electronegativity. The greater the electronegativity difference, the more strong the bonds will be. Okay, so that makes sense. If one attracts a lot better than the other, then the bond is going to be a lot stronger. Okay, however, if it is very large, then the electrons are considered to be transferred instead of shared. And remember, in the beginning, I said if it's transferred, it's called an ionic bond. So this occurs when your electronegativity difference is greater than 1.2. Leading on from electronegativity, we're going to deal with polar molecules. So the shape of the molecule determines the effect the polar bonds have. So if the polar bonds are balanced by other polar bonds, then it's going to be a non-polar molecule. So this will be seen in symmetrical molecules like CO2 and CH4. However, if there are polar bonds and it is a non-symmetrical molecule, you will have a slight positive and slight negative side in the molecule, and so you will get a polar molecule, such as NH3 and H2O. Okay, so that's why it's important to know the shapes of molecules. And this is determined by the number of bond pairs and lone pairs. I'm not going to go into a lot of detail on this, just give you an overall picture. So the shapes of the molecules affect your boiling point, your melting point, the physical properties, and the intermolecular forces between the molecules. So we have 4 basic shapes: linear, angular, pyramidal, and tetrahedral. So linear, for example, are your H2, N2, CO2, and HCl. So this is mostly when the 2 atoms have bonded together, and this can be symmetrical or asymmetrical. So for example, H2 and N2 and CO2 actually are all symmetrical, whereas HCl is asymmetrical. Angular, this is generally when there are 3 atoms that are not arranged linearly and the 2 shared electron pairs, such as H2O and H2S, and generally these are all asymmetrical. Okay. Pyramidal, that is when you have 4 atoms, 3 shared electron pairs, and 1 lone pair, so NH3, and this is asymmetrical, because when you think about the shape of NH3, you have a lone electron pair, which will be negative, so it will skew the polar and it won't be symmetrical. Whereas tetrahedral, you have 5 atoms and 4 shared electron pairs, such as CH4, and so it is symmetrical. Okay, another concept that is pretty important, and the reason why I'm going to answer this next is because I am going to give you a lot of time to really work through these concepts and consolidate them. So bond length and bond energy. So the bond length, measured in picometers, is the distance between the centers of the bond atom pair. The stronger the bond, the smaller the bond length. So small atoms form stronger bonds as a result of the greater attraction towards the nucleus of a small atom. The atomic radius decreases towards the right in a period and increases towards the bottom of a group. Make notes in your periodic table. It'll be its most stable when the repulsion and attraction forces are equal. Bond energy is measured in kilojoules per mole, and this is the amount of energy required to break the bond by overcoming the force of attraction between the atoms or energy released when the bond is formed. Generally, bond energy decreases as bond length increases. Multiple bonds are stronger than single bonds, and that makes sense even if you just think of normal application. And when the sum of the energy required to break the bond is greater than that released to make new bonds, the net value will be positive and you'll get an exothermic reaction. However, the same applies in the exact opposites and you'll get an endothermic reaction. So just to quickly recap, the bond length is the distance between the centers. The bond energy is the amount required to break that bond. Okay, Multiple of them are stronger, and generally if your bond energy increases, your bond length will decrease, because if they're closer together, they'll be a lot more difficult to separate. Okay, so we've got question 3 on molecular and shape and polarity that I would like you to attempt just on what you think these are. Give an example, say the polarity of the bond and the polarity of the molecule. Just consolidate everything I've said into a more visual, simplified form. And if you have any questions, please bring them up in the Q&A. And then this question 4 is on your bond energy. So just identify the most unstable with reasons, the general relationship, which bond is the strongest, and explain the difference in bond. Okay, so this is just to, if you also have any questions, feel free to bring it up in the Q&A, but I'll give you some time to do this and I will go through it. Right, so I hope you had a nice chance to just make a brief summary on question 3 and then try question 4. Okay, so we're going to go through both. So for the first one, this is basically just kind of getting your brains wrapped around all the concepts we talked about. So we've got molecular shape and polarity. Okay, so for the first one, we've got a small molecule bonded to a big molecule. So our molecular shape would be linear because it's in a straight line. Okay. The second one is one big molecule joined to two little ones, and that is something you would know as angular because it's made an angle. The next one, you've got the 3 and you've got the 1 on top. So generally what will happen with this one is there'll be electrons on top, and that's why all those 3 are pushed down to the bottom. Okay, and that will be called your pyramidal shape. Then your next one, you've got 1 in the middle and you've got 4 on top that are equally spaced, and that is called tetrahedral, because if you draw all of them, you'll have a tetra, which is 4. And then your last one is also linear. The formula of a substance with this shape. We've got the first one, we can say HCl, for example. We know it has to be 2 separate molecules, so don't say H2 or N2, but you could say potassium bromide, anything that isn't the same, basically. The next one, we've got 1 joined to 2, so we have to have 2 separate ones. So H2O, for example, or you could use any other example where there are two molecules joined to 1 and they're not the same. Okay. Then your next one, an example would be NH3. Okay. Any other one, as long as there's 1 and 3. The next one, I'm going to go with CH4. And the last one, I'm going to go with CO2. Okay. Next, it's the polarity of the bond. So this is where you have to bring out your periodic table. Look at your electronegativity differences. So, for example, we've said hydrogen and chlorine. So there is an electronegativity difference there. So therefore, the bond is polar. Okay. Then linked to that, the polarity of the molecule. So because it's asymmetrical and there's a polar bond, it is therefore a polar molecule. The next one, so I selected H2O. There is an electronegativity difference, so therefore the bond is polar. If you look at the shape, it's not really symmetrical, so it is therefore a polar molecule. The next one, nitrogen and hydrogen do have an electronegativity difference, and so the polarity of the bond is polar. And therefore, because it's also asymmetrical, because the top will be negative and the bottom will be positive, it is a polar molecule. The last one, your carbon and your hydrogen have an electronegativity difference, and so they all have polar bonds. However, it is a symmetrical molecule, and so it is therefore a non-polar molecule. The next one, carbon and oxygen, also have a polar bond. However, it is symmetrical, and so it's a non-polar molecule. Okay, question 4. Identify the most unstable bond. So a bond that is unstable means the molecule is very likely to break. So that will only happen when the bond energy is very low. So we're going to find our very lowest one, and that is nitrogen to nitrogen single bond. And the next question, what is the general relationship between the size of the atoms and the bond energy? So remember, if we've got an atom, the size of the atom, if it increases, your radii get bigger. And therefore, your bond length from the center of one to the center of the other will get further and further apart. And remember what I said, when your bond length increases, your bond energy decreases. Therefore, if you increase the size of the atoms, you're going to decrease the bond energy. Okay. Which bond is the strongest? So having a look at this one, the strongest is 945 kilojoules per mole of bonds, okay? And that is your triple nitrogen bond. And the reason why it is the strongest is because, first of all, there are 3 bonds, which make it a lot more difficult to break, and the fact that it has such a high bond energy. Explain the difference in bond energy. You generally won't get two similar questions like that. But basically, the difference between the triple and the single is 945 minus 158, which is quite a substantial difference. And that's just because the bond is a lot more difficult to break as a triple bond. And then your double to your single is just less than double. So it is still, your double bond is still greater because it's obviously multiple bonds that take more energy to break. However, it's not 158 to 945. Okay, so it's a slightly weaker multiple bond, in other words. But as you will see, a single bond to a double bond will be like a little bit of an increase. And then the more bonds you get, the higher it will be. Okay, so I didn't want to add any more further concepts because this kind of sums up this whole main area, and then next week we can go on to further topics. So I wanted to introduce something called rapid fire. I think this will be beneficial. So what I'm going to do is I'm going to put up a couple questions, and then I'm going to put on a countdown of about 15 seconds, or depending on how long the question takes, and then I'm going to wait for you to answer them, and then I'm going to give you the answers. So this is just a little more interactive. Okay. You don't have these in your worksheets just because I did want this to be almost like a quiz that you haven't seen these questions yet, and just so you can keep track and see if you've covered everything. Question 1. The distance between two adjacent atoms in a molecule. Question 2. A type of chemical bond that involves the sharing of electrons between two atoms. Question 3. A measure of an atom's ability to attract electrons to itself in a chemical bond. Question 4. Which one of the following best describes the bond formed between a hydrogen ion and an NH3 molecule? Question 6. Given the following Lewis diagram, where X and Y each represent a different element, how many valence electrons does X have? How many valence electrons does Y have? Which elements could X and Y represent? Okay, and that brings us to the end of this second lesson. So I know it probably wasn't very hard, and it was just a lot of basic understanding, making sure you do have the basic foundation so we can build on in the future. And I really hope you enjoyed the examples I set and the rapid fire at the end. Hopefully that made the little push at the end worth it. So we've come to the end. There will be a Q&A after this. So if you have any queries on anything that has come up, or if there's anything you would like me to work on for the next one, please make a note of it and I'll be happy to answer them. And other than that, this has been Tutorbox Live, and I hope to see you for the next one. Stay safe, everyone, and see you next time.